Hello and welcome back to my videos on perfect numbers. In a previous video I briefly discussed perfect numbers and how to form them, and I gave a few examples of some perfect numbers. Now I want to go into a bit more detail. So if we have a perfect number n, then n is equal to 2 to the power of p minus 1 times 2 to the power of all to the p minus 1. Now these two components make up a perfect number and they're very important. The one I want to look at and focus on at the moment is the one on the left, 2 to the p minus 1. So that's this one here. Now in around 300 BC, Euclid discovered that if this number here, 2 to the p minus 1, is prime, then n is a perfect number. And that is the only condition. That is a sufficient condition. It's a necessary condition, but it's also sufficient. That has to be prime and we're in business. Then we can get a perfect number once we know p. Now as a consequence, when 2 to the p minus 1 is prime, then p will be prime. That always happens. It's not the other way around, unfortunately. There are values of p for which 2 to the p minus 1 is not prime. We will look at that in a moment. So basically we need to find numbers of the form 2 to the power of p and then minus 1 which are prime, and we will automatically find a perfect number. Around a couple of thousand years later, Euler discovered that all even perfect numbers are of this form, 2 to the power of p minus 1 times 2 all to the power of p minus 1, and then that became known as the Euclid-Euler theorem. Now this 2 to the power of p minus 1, being a prime number, has a special name in mathematics. It's known as a Mersenne prime, which was discovered by a French mathematician, Mersenne. And as I said earlier, when that is prime, then p is prime. Let's look at an example and a counterexample. So let p equal to 5. P is prime, as we know. 5 is prime. 2 to the power of 5 minus 1 equals 31 is a Mersenne prime, because 31 is prime. So 5 doesn't necessarily have to be prime, but 31 has to be prime. The answer has to be prime. However, as I said, that p will always be prime in that case. If we have a Mersenne prime, then the p that formed it will be prime as well. And a counterexample, 2 to the power of 11 minus 1. 11 is prime, but 2 to the 11 minus 1 equals 2047 is not prime. Therefore, 2 to the 11 minus 1 is not a Mersenne prime. 2047 is a composite number. It can be made up of 23 times 89. So it has two prime factors. So that's a little bit more detail. I'm now going to show you a few quick examples of Mersenne primes and how they're connected to perfect numbers. Okay, so now I want to talk a little bit more about Mersenne primes. So we have n equal to 2 to the power of p minus 1 times 2 to the power of all to the p minus 1, where 2 to the power of p minus 1 is prime, and that implies n is perfect. So 2 to the power of p minus 1 here is what's known as a Mersenne prime. Example, 2 to the power of 5 minus 1 equals 31. Once we know or find a Mersenne prime, we automatically get a perfect number. Now let me demonstrate that with a few examples. So the first perfect number is 6, which equals 2 squared minus 1 times 2 to the power of 2 minus 1, and that's equal to 3 times 2, which is 6. 28 equals 2 to the power of 3 minus 1 times 2 to the power of 3 minus 1 equals 7 times 4, and so on, all the way down to 33,550,336. Those are the first 5 perfect numbers that we know in the left hand side here. So I've written perfect with an arrow, so these are all perfect. And then these numbers here, this column here, these are all Mersenne primes. 2 to the 2 minus 1, 2 to the 3 minus 1, 2 to the 5 minus 1, 2 to the 7 minus 1, and 2 to the 13 minus 1. These are all Mersenne primes. And you'll notice the exponent of 2 is a prime number. And that's always true. Once we have a Mersenne prime, this exponent will be prime also. But if the exponent is prime, that doesn't mean 2 to the prime minus 1 will be Mersenne prime, as we discussed earlier. And then these numbers here are just powers of 2. So once you write the number out in its raw form, so you get 3, 7, 31, 127, these are all Mersenne prime numbers. And this is it written in the form 2 to the p minus 1. And then these are just powers of 2. So then another thing we can do is we can write it in another way, or we can think of it another way is, so if we let q equal to 2 to the p minus 1, so that's a Mersenne prime, so q is a Mersenne prime, then n is equal to 2 to the p minus 1 times 2 to the power of p minus 1 in the exponent. So this is our perfect number, n is a perfect number. So n can be written as q times q plus 1 over 2. So the q plus 1 over 2 comes from, when we add 1 to q, we get 2 to the p, and then we divide by 2, we get 2 to the p minus 1, just by your rules of indices. So I think you can see that for yourself. So that means n is perfect. So when n is perfect, this will hold. You'll have n equal q times q plus 1 over 2. And you'll notice something about that. You'll notice that that is equal to the sum to n, or the sum to q, sorry, of the first q integers. So let's suppose we have like 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, where q equals 7, for example. So n here is equal to 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, where q equals 7. So you're adding them all together, and the well-known formula for adding the sum to n of a set of integers going from 1 to infinity is n times n plus 1 over 2, or a half n, n plus 1. You would have learnt that in other courses. So we can apply that here. So that means that if you give me a Mersenne prime number, say 31 or 127, then I can tell you that the sum of the integers from 1 up to that Mersenne prime number will equal a perfect number. So the sum from 1 to 31 will equal 496, which is perfect. The sum from 1 to 3 is 6, which is perfect. The sum from 1 to 7 is 28, which is perfect. The sum from 1 to 127 is 8,128, which is perfect. And the sum from 1 to 8,191 is 33,550,336, which is also perfect. So that's another way to think about it. It's another way to think about perfect numbers. So the challenge is not so much to find perfect numbers, the challenge is to find Mersenne primes, because there's a one-to-one correspondence, which Euclid and Euler proved. Well, Euler did most of it. Euclid discovered Mersenne primes. He discovered that when you have a Mersenne prime, you can find a perfect number from it, and then Euler discovered that there's a one-to-one correspondence. It's an if and only if relationship. So once we have a Mersenne prime, we get a perfect number for free, and vice versa. So every perfect number is associated with a Mersenne prime, and vice versa. Okay guys, so I hope you enjoyed the video. Stay tuned for more videos. If you enjoyed the video, please like, share and subscribe.